Hello and welcome to Physics for People with Better Things to Do. I'm Ricky and today's episode is going to be on fluids. So the first thing you need to know when learning about fluids is the idea of pressure. Pressure actually has a fairly simple definition, and that is a force over an area. With such a simple definition, it's easy to see that pressure can be found everywhere in your everyday life. For example, you may have heard that when on a frozen lake, you should lay down to spread out your weight. The reason this works is because under immense pressure, the ice will crack. So if you exert your weight over a greater area, the ice will be much less likely to crack.
For pressure is pascals, which conveniently is equal to 1 Newton over 1 meter squared.
However, there are some more atypical units used for pressure. For example, there's the atmosphere. 1 atmosphere is equal to 1.01 times 10 to the 5th pascals, and it is equivalent to the pressure exerted by the atmosphere of Earth at any given time. The imperial unit for pressure is pounds per square inch, or PSI, which just means that 1 pound of force is exerted over 1 square inch of area. Another unit you may see is mmHg, or millimeters of mercury, and this unit comes from the use of a barometer, which is a device that measures pressure. It just represents how far up a tube mercury is forced by an external pressure. Now, these definitions of pressure can be used in any scenario. However, there is an equation for pressure that only works with fluids, and that is P equals rho GH. The P in this equation represents our pressure, the rho represents the density of the fluid, the G represents our universal constant of gravity, and our H is actually the depth of which the object is submerged. Some terms you may hear when discussing pressure is gauge pressure and absolute pressure, and there's one very important difference between the two. Gauge pressure is the pressure that is physically measured in a system. These gauges that we use to measure pressure are automatically adjusted to the 1 atmosphere of pressure exerted by air. Therefore, we call this gauge pressure as it does not include the pressure from air. However, absolute pressure does take into account the 1 atmosphere of pressure exerted on us by air. Now, the first major law that you're going to run into when discussing fluids is Pascal's law. Pascal's law says that at any 2 points in a static fluid, meaning it's not moving, the pressure is the same. Pressure can be thought of as a push that makes fluids move. So if you have 2 points of different pressure, then the fluid in the higher pressure is going to move toward the area of lower pressure, which thus makes it no longer static. So if you have a static fluid, then it must have equivalent pressure everywhere. Let's take this problem for example. A U-shaped tube is partly filled with water and partly filled with another liquid with an unknown density. Both sides of the tube are open to the atmosphere. And it's important to note that the density of water is 1,000 kilograms per meter cubed. Let's say the problem is asking us to find the density of the unknown fluid. The first step in a problem like this is to draw a reference line from which you will be measuring your heights. For this problem, I will be using the boundary between the two fluids as my reference line. As you can see, the problem gives us that there are 0.3 meters of the unknown fluid on the left side of the tube, and we can use the information given to find that there are 0.25 meters of water on the other side of the tube. Our next step in this problem is going to be to set the pressure on both sides equal to each other. So we set our rho 1 times G times H equal to our rho 2 times G times H. Luckily, in these problems, gravity cancels out. Then we can just plug in the information that the problem gives us. For our rho 1, we can plug in our 1,000 kilograms per meter cubed, and for our H, we can plug in 0.25 meters. On the other side, we can plug in our 0.3 meters of our unknown fluid. Then, by solving this equation for rho, we can find that the density of our unknown fluid is about 833 kilograms per meter cubed. Now, an extension to this problem may be to solve for the absolute pressure at the bottom of the tube. Now, if we recall our definition of absolute pressure from earlier, we can say that absolute pressure is gauge pressure plus 1 atmosphere in whatever unit it may be. And since we know that pressure is the same anywhere in a given static fluid, we can use either the right side or the left side of the tube and get the right answer. However, for the sake of simplicity, I will be using the right side as there is only one fluid to deal with. Pressure is a scalar, meaning we don't need to take into account direction when adding together two pressures. So, to solve for our pressure at the bottom of the tube, we can add together our 1.01 times 10 to the 5th pascals from the atmosphere and our rho GH from our water. We can plug in 1000 for rho, 9.8 for G, and then our 0.45 for H, as we are taking into account the whole depth of the tube. By evaluating this equation, we can find that the pressure at the bottom of the tube is equal to 105,410 pascals. That's pretty much it for this type of problem, but there is another type of problem that you may see. Let's say a hydraulic lift raises an elevator weighing 2,500 newtons. If the problem asks us to find the minimum force needed to lift the elevator, we can actually use our basic definition of pressure to solve the problem. First, we find the cross-sectional area of both of the pipes, meaning we use the radii given to us to find the area of a slice of each of the pipes. Then we can set up a proportion that says that the input force over the area of the input piston equals the weight of the elevator over the area of the lift piston. Then, by plugging in the weight of the elevator, the area of the lift piston, and the area of the input piston, we can find the minimum force needed to lift the elevator. After rearranging the equation, we can see that this force is about 13 newtons. Another important aspect of fluid statics is the buoyant force. The buoyant force is the force applied by a fluid that is being displaced by another object. The equation for buoyant force is rho Vg, but it's important to note that the rho is not the density of the object, but rather the density of the liquid. The V represents the volume of the fluid displaced, but luckily you can just use the volume submerged in the fluid. Let's say a rubber ball with a volume of 1 meter cubed and a density of 500 kilograms per meter cubed is placed into a bucket of water. How would we find the volume of the ball that's submerged in the water? Luckily, we are able to use the ratio of the density of the object to the density of the fluid in order to find how much of the volume is submerged. In this case, 500 kilograms per meter cubed of the ball over 1,000 kilograms per meter cubed of the fluid results in a fraction of 1/2. This means that 1/2 of the ball will be submerged in the water. So we can take our volume of 1 meter cubed and divide that by 2 to get 0.5 meters cubed. Then we can plug in our 1,000 kilograms per meter cubed for our rho, our 0.5 meters cubed for our V, and our 9.8 for our G, and we can get that the buoyant force is about 4,900 newtons. That's about it for fluid statics, but there's a whole different area of fluid dynamics. The first important concept when discussing fluid dynamics is the idea of continuity. Continuity is basically the conservation of mass in disguise. It says that in a continuous system, at any 2 points, the flow rate must be equivalent. Flow rate is simply defined as volume over time. However, through some unit analysis, we can find that the flow rate is also equal to the cross-sectional area times the velocity of the fluid. Continuity itself isn't very useful other than describing why water shoots out faster from a hose when you cover part of the nozzle, but when used with Bernoulli's principle, it can be quite useful. Bernoulli's principle is pretty much just the law of conservation of energy in disguise, because physicists love reusing laws. Bernoulli's principle can be represented using this equation, and you may recognize some familiar terms. The P represents pressure. The rho GH is comparable to gravitational potential energy, and the 1/2 rho V squared is comparable to kinetic energy. Let's say an enclosed tank has a diameter of 80 centimeters, with a smaller hole drilled on the side for the water to flow out. The tank is pressurized to 1.25 atmospheres in order to provide pressure for the water to flow to an off-the-grid scout camp. The water level in the tank is at about 2 meters, and the height of the hole is about 0.5 meters. If the problem asks to find the speed of the water leaving the tank, we can use Bernoulli's principle. The first step when solving a problem like this one is to convert all of our information given to us in the problem into standard units. Bernoulli's principle requires SI units, so it's important to convert our values into SI units before using the equation. Then, Just like using Pascal's law, we draw a reference line. This reference line is going to be at the height of the hole. Then we can determine that there is 1.5 meters of water above the hole. And so into our rho GH part of the equation, we can plug in our 1,000 kilograms per meter cubed, our 9.8, and our 1.5 meters. Since the problem specifies that the hole has a much smaller area, we can assume that the velocity of the water within the tank is 0, and thus the kinetic energy term cancels out. Then we can set that equal to our 1/2 rho v squared plus our 1 atmospheric pressure. We do not include the rho GH term in this because the water is now at our reference line, and thus it has no height. We include our 1 atmosphere of pressure converted into pascals because the water at the other side of the hole is going to be exposed to air. Then we plug in our 1,000 kilograms per meter cubed for our rho, and we solve the equation for V. Once we evaluate this equation, we find that V is about 9 meters per second. So that's about it for fluids. Thank you guys so much for watching, and I'll see you next time on physics for people with better things to do.